I am building a distributed computer system for a CubeSat, multiple boards working together as one machine. Over time, I realized I don't need to start each board from scratch. I can use functional groups by putting them on hierarchical KiCad sheets. These sheets are my hardware subroutines. They make CubeStack modular, repeatable, and fast to develop. Today, I'll walk you through 10 of these. Why they exist, what they do, and how they fit into the bigger system. Every CubeStack board needs a way to show what's going on. So I break out serial wire clock and data for programming and debugging, the boot and reset lines, the UART1 for communication and programming, and 5 LEDs, green, red, and 3 yellow or orange. Every board uses the same 2 headers for serial data and UART. The MCU pin assignment of course changes per board, but the sheet stays the same. CubeStack boards run unattended. If something locks up, I need a guaranteed recovery path. This sheet handles external Watchdog timing, a wake-up signal that must be acknowledged, and it resets the MCU if that signal isn't acknowledged in time. Here's our customization trick. The wake-up interval is set by a resistor. To give each board its own interval if necessary, that resistor sits outside the sheet, connected through hierarchical labels. During firmware development, flashing the MCU requires a little ends with reset and boot lines. A simple sheet with a switch and pull-up resistor handles boot, and unless the watchdog is placed, another switch and a capacitor handle reset. USB is always the same. A USB-C connector and pull-down resistors on the configuration channel lines. This sheet is a drop-in front end for any CubeStack board that needs USB. And they all need USB for programming and logging. And yes, eventually I should add ESD protection. CubeStack modules talk over a shared bus. This sheet defines the connector, the signals, and how power is distributed between boards. We have a 40-line PC104 bus connector, an unswitched battery line, switched battery lines, switched 3.3 volt regulated lines, 2 full CAN buses, and of course lots of ground. CAN is the backbone of CubeStack communication. This sheet handles transceivers, termination, and protection. For simplicity, I use the Texas Instruments TCAN3414, which only needs 3.3 volt rails. If necessary, we can mark the termination resistors as do not place. Each board needs MRAM for configuration data. Most boards also have 1 or 2 flash chips for data buffering and remote firmware updates. This sheet makes storage plug and play. Power gating is essential for CubeStack modularity. Boards need a way to switch subsystems on and off. This sheet controls subsystems power rails cleanly and safely. Each instance controls 2 lines. This sheet let me measure and control power rails over I2C. It's how the CubeStack monitors subsystem health. An I2C GPIO expander enables and disables the dual switches we just saw, so any sheet can include others. An INA226 measures current and voltages ahead of the switches and alerts the MCU should too much power be drawn. CubeStack needs many regulators, 3.3 volt for cores and peripherals, 5.1 volt for battery management, 2.8 and 1.8 volts for cameras. It's the same regulator block every time, just with different set points. I customized the voltage divider using hierarchical labels, and the rest of the sheet stays identical. These 10 sheets are my hardware library. Define them once, test them once on one board, and drop them into every other design as needed. They make CubeStack faster to build, more reliable, and easier to maintain both in hardware and firmware. We will see these designs again in upcoming episodes, when we take deep dives into CubeStack boards. Thanks for watching. See you next week.